My name is HanShe Lim from James Cook University, and I'm the main investigator for the project, Modeling Unseen Flow Pathways. This project examines the role of paleochannels, or ancient river systems, in moving water through agricultural landscapes. We were interested in how they interact with surface drainage to move nutrient-rich water into the Great Barrier Reef. Project produced the results of modeling experiments where we ran the model virtually on a computer, where we coupled a crop model with a groundwater model to see how much water moves through paleochannels. We also produced maps of paleochannels and surface drainage to look at the interactions between these features in the agricultural landscape. This project was a success for me because it allowed the opportunity for me to collaborate with a wide range of scientists from different Queensland government departments and also with traditional owners.
Second presentation, and we're going to explore the past paleochannels by going north to North Queensland around the Cairns region. I'd like to welcome HanShe Lim from JCU to the floor. Come on up, HanShe. There we go. The technology has worked. Excellent.
Good morning, everyone. Thank you for your time. I'd just like to present this project that we've completed. So it's completed now, and it was done with a large number of collaborators, including Tony and his team of modelers. I'd like to mention Felix and Rowan Eccles. They were really great. And also working with people from other Queensland government departments, so namely Department of Resources and Agriculture and Fisheries. So without them, we couldn't do this project because we were using the data that they obtained from previous projects. And finally, I acknowledge Jerrigan because they are the traditional owners of the land where we worked, and they ran the engagement event to let the various stakeholders know the outcomes of this project. So what we were interested here is what we call unseen flow pathways. And the flow pathways that we are interested in are what we call paleochannels. So we often think of paleochannels as abandoned river channels, but they might not necessarily be abandoned because they're buried. We can't see them, but they may be still active doing their thing underground. So when we look at this landscape here, which is very typical up north, just south of Cairns, you'll see a lot of agricultural land, paddocks, agricultural drains, roads, and so on, if you can see them. And if you look hard enough, you can see probably some river channels, old river channels that don't seem to be flowing on the surface anymore. So they're up there, and if you can't see it, they're somewhere in the middle of this slide.
You can probably use the mouse.
Can I? So around here, so you can see that this would be examples of old river systems that are buried. So they used to be on the surface previously. And just to show you where our study site is, Cairns is up there in the north, so in the Wet Tropics, and our study site is over here, shown in the red shape here, which is in Babinda. So it's a big sugarcane growing area. It's also been identified by the GBR modelers as a hotspot of DIN production. So it's an area of concern. So what we know is that when we look at these old river channels, they're buried with material that tend to be more conductive than the surrounding soil. So that means that if water gets into these old river channels, then it's very likely that they form, water will flow preferentially in these routes out into the sea, which isn't very far away from these sites. You can see how close Babinda is to the coast. So what we're interested in is how do we represent these flow pathways in the model, and how can we represent the interactions between these buried flow pathways with our surface drains, which is an interesting problem, but difficult. Okay, so does it matter I'll show you all the questions first. Does it matter? Yes, these flow pathways, the buried flow pathways, are important because the farmers know that when these systems exist on their paddocks, it's likely that these areas tend to have poorer crop yield. So we don't really want that, because poorer crop yield means that the farmers are likely to put more nutrients of fertilizers, which then leads to increased nutrient export. So then we know that based on what the farmers tell us, that there's quite variability in the soil properties, just even on a paddock scale. So paddock soils versus paddock parts, which have these buried river channels. So first, they have the potential to affect your crop yield. Second is that if water gets into this preferential flow pathways, then they form a fast way for probably nutrient-rich water to get out to the sea, which is not ideal for us. So then we're interested in how these paleochannels affect the flow of water, so the amount, speed of water, first step, and then second, their impacts on nutrient transport. And once we understand this better, then we can then come up with better management solutions to deal with the issues of water quality problem that is very important in this site. Now, the other thing that we are actually thinking about, here you can see, this is I'm having a bit of problem with the mouse, but yeah, that's the buried river channel system here. And this is expected because it's a floodplain area. So we know that the rivers move around quite a lot over time. So what is really important in this project also is because a lot of the GBR models are modeling at a large catchment scale. They are unable to model at this scale here, at a paddock scale and a sub-catchment scale. And so we thought that perhaps this project can provide that spatial link or the scale link between paddock scale to the GBR models, which are the largest scale hydrology and water quality models. Okay, so if we look at this picture here, so basically what we're trying to do is to model a landscape with paleochannels. So if you look at the top right-hand side here, you can see a few paddocks. The blue arrows show the flow of water from one paddock to another via the agricultural drains that the farmers have put in. Now, if we look at a cross-section across the paddock, and you can see that this is what we have. We have crops, and the crops that we are modeled here would be sugarcane. And the cross-section being an agricultural drain there, and the flows of water shown by the blue arrows. So in these systems here, we have lateral flow of groundwater. So sometimes groundwater discharges into the drain. Sometimes it's the other way around, especially during the wet season when this area floods. And you don't really want to go there because crocodiles come up out of the creeks. And we've actually seen them before. So this is ideal paddock without a paleochannel. But if we have a paleo channel that goes across the paddock, then what we can see is that the paleo channels here at the bottom left-hand corner, and you can see that water, subsurface water or groundwater can be diverted, can be diverted into the paleo channel and move away, preferentially away from the drains or maybe meeting the drains further down, okay? So how do we model a system like that? Because it's really complicated, because some paddocks have no paleo channels, some have paleo channels. So we need a complicated model. So in order to come up with a framework to model this sorts of landscape, we did a big literature review and then decided that, okay, fine, we need a model that can model the hydrology of the crop system, so the sugarcane crop, and vertical drainage of water down into the subsurface. And then we needed a more complicated subsurface groundwater model to model this diverse flow of water, which can go in any directions. So because we're in Australia here, we found that APSIM is quite a suitable model because it's widely used in this country for crop modeling. And we can look at various models where we can look at nutrients and water flow, okay? And then because APSIM models water as vertical drainage down to below the ground, we decided that the subsurface flow of water would be better modeled with another more specialized groundwater model called ModeFlow. We can look at subsurface water flows in 3 dimensions. So then we thought, okay, we need to couple these 2 models together. And so we got Tony and his team to do the hardcore modeling work. So if we look at this here, you can see that the squares, the red squares represent different points in the paddocks. And each of these 3 red squares have different, the water can flow slightly differently on this, in these 3 squares. Now, if the square was in a paleochannel, it has many options to flow faster within the paleochannel to a downstream location. Whereas if it was here on this part here, on the right side, the red square, most likely the water surface and subsurface water will flow into a surface drain. So very complicated system. So we decided to try coupling EPSIM and ModFlow together to try and capture the crop water use and drainage of water from the crop, the sugarcane crop, and then subsequently model the subsurface flow of water. And so this is, for example, what we decided to do then for this approach is to use the modeling framework of a coupled model, crop model with ModFlow, a subsurface model, and do virtual experiments at the paddock scale. So we start small, at the small scale. And you can see this is a paddock here, if you follow my mouse, and you can see the paleochannel there. So something like that in this paddock on the left. So because we don't have much information about the paleochannels, what we decided to do is to run virtual experiments, so up in the computer world. Both Felix and Rowan were crucial in doing this. Basically, what they did was they tried to couple EPSIM and ModFlow together using an imaginary paddock, which you see on the right. So it's not very interesting, it's just a rectangle. But we look at water flows in the X, Y, and Z dimensions. And to do this, what we try to do is to model 3 scenarios. One scenario, a paddock with no paleochannels, such as the one here. So just the green part here is just paddock, normal paddock agricultural soils of that region. The other 2 scenarios are having paleochannels incorporated. One, the paleochannel on the surface, as shown on the left, and a paleochannel on below the ground, so buried below the ground. And what happened was we varied they varied the conductivity of the soils so that the paddock soils and the paleochannel soils were different. Okay, the paleochannel soils had a higher conductivity, means water can move much faster. So this was just simple experiments. The paleochannel ran parallel to the agricultural drains. Okay, but we know that this is not all paleochannels follow this rule. They do what they like. And very simple experiments done, we found that when the paleochannel was on the surface, as shown here, this is the yellow paleochannel soil. Apologies. The subsurface flow that came out of this paddock increased by 3.5% as compared to a paddock that didn't have any paleochannels. So 3.5%, not very high. If we had a paleochannel that was buried, shown here, the subsurface discharge, total discharge, sorry, not subsurface, but discharge that came out from this paddock increased to 4.4%. So it would seem like if you had buried paleochannels, then flow coming out would be higher, slightly higher. So these are just virtual experiments. How do we know if they're real? They could be imaginary. It's just up to the computer to do what they like, especially with artificial intelligence, could be a bit dangerous. So what we decided to do is that we need to parameterize these models. So we went back to the field and looked at actual field data. So you can see that this is our study area. The black line represents the Babinda swamp drainage area. The blue lines represent all the agricultural drains that the farmers and the drainage board have put in. And the pink represents the locations of these paleochannels that were mapped by a previous project. And if you are very observant, you'll notice that the middle area is there's no information. And that's because the previous project only focused on sugarcane areas, whereas these areas here are used for grazing. So that's a data gap. So some of the things that we looked at with the information that we obtained from our collaborators were just looking at spatial relationships in terms of area coverage, length, distance of paleochannels in the paddock and its relationships with surface drains or with rivers. So for example, we looked at the coverage of paleochannel within each paddock, shown by different shades of peach and brown. And we found that some paddocks had no paleochannels, Whereas some other paddocks, especially those close to the edge here, which is where the Russell River is located, they had a high percentage coverage of paleochannels. We also looked at how paleochannels intersected with the surface drains, because then you have an interaction between subsurface water and surface water. And we came up with maps like that. Right, so basically tells us the spatial configurations of paleochannels that you can find in the field. I'll skip this, too much information. So this was a pretty interesting project. It was only 1 year, and we managed to model 3 virtual experiments and did lots of spatial analysis. But we would like to do more virtual experiments with Tony and his team, and also to work with our collaborators from Department of Agriculture and Fisheries, who are putting up some monitoring sites where paleochannels exist, so to get more field data. And we hope that, you know, we can find some funds to do this in the future. So thank you very much. Before I end, I'd like to thank Jenny and the team for the support they gave for this project. It was really helpful. Yes.
Like last time,
Yeah.
spoke with earlier channel, we went back to the so every different thing, each in river system.
Yeah.
It'll be interesting to see what data. There probably is no data really, other than evidential artifacts and stuff that may be associated with that system. So it'd be interesting to see how the modeling goes with other projects around, just like I sort of work with different groups years and years ago with the in nature. The system creates a done and you will continue to run that in. But if we, my country at the moment is very dry, more of the river system, you know, filled it up and no longer something that they used to. But to me, is to understand the data and the evidence that come with it to show that, because we only talk about just the little existing topics that you have, especially Queensland, really just trade routes and water routes, what systems are like to them. So it'd be interesting how popularity is mapped across, especially that this is being done.
Can we talk about this later during tea time? Definitely, we've got the traditional owners of that site involved in this, and their rangers are actively helping out with the monitoring of these sites. And they actually do have artifacts as well, as you mentioned, but I'm not sure yet how we can actually say where these artifacts. No, that's for another project. That was Guju Guju. Yeah. Oh, no. Yeah, I won't talk about the yeah.
Any other questions? Just introduce yourself before.
Oh,
maybe clarification. The surface paleochannel identity human body and all channels with similar connections.
Yeah.
Like if that's the second thing is I know when we drill things, the components are very, very resistant on bodies. So I was wondering how much field data you had on the assumption around different hydraulic conductivities versus the basic facts.
So the guys who did the mapping from Department of Resources, they took soil samples as well. And what happened in this project was they only the identification of the paleochannels was based on electromagnetic induction mapping. So those paleochannels that you see in this map were visible to the instrument up to a depth of maximum about 1.5 to 2 meters. And that probably falls just the upper extent of the paleochannel. We don't know how deep it goes. But at the same time, they also took a lot of soil cores from around. So they identified differences in the properties of what they call paleochannel soils versus the non-paleochannel soils of the different paddocks. And so they found that generally these paleochannels will tend to have wetter soils. They did not do any hydraulic conductivity tests. Yeah, but it was based more on field observations from the soil scientists. So the next step would be they're carrying out some field monitoring activities in paleochannel sites where they will be putting in bores and taking soil samples, and we can run experiments, field experiments in those sites which we think are where paleochannels are located. Yeah. Did I answer your question? Sorry, did I? Sorry, did I?
You said that the problem has
Mm.
if go after to make it each other or whereas actually one then like capacity.
I believe so. I didn't do this virtual experiments. It was Felix who did the experiments for us. Felix from Alluvium. I believe he ran AppSim with the R code and then used the outputs to go into ModFlow. But these are very preliminary and early experiments because we were just trying to see if we could even take the outputs from AppSim into ModFlow. So there's more work that has to be done later on. So it's just very first baby steps.
Can I ask a question?
Yeah.
What do farmers know of these landscapes?
Oh,
How
they do, because the crop
do
yields,
they behave differently?
yeah, the yield for a sugarcane on soils which are what they call paleochannel soils are poorer than the yield they get from soils which don't have paleochannel infill material. So the farmers do know, and sometimes when they're digging, they can identify where they dig out. If it's paleochannel soils, it fills up with water very quickly. So they do know where these are on their paddocks.
Do they manage the landscapes differently as a consequence?
I'm not sure about that. I will find out. I'm sure they do.
So we've probably got time for one more question before we'll move on to our last presentation before morning tea.
Yeah.
If you could introduce yourself.
Oh, sorry. The farm generation, so we have all the farmers in Queensland. Ideally, not all of them are. I understand how the patio channels work, but there are ones that do, and it actually interferes with the crop development. So you will see stunted growth in some sugarcane in those particular regions. There is no way of changing the way that they do manage the whole area to accommodate those different channel areas, but they do impact on their crop growth from my understanding. Certain areas that I've been working in the vertical.
So they leave it as it is then? Too hard to manage.
Well, they've also got other issues with regards to rising groundwater and some developments that are also impacting. So it's very hard to determine whether it is just that or it's a combined effect. I would say the latter, but they don't change the way in which they farm because of that particular area and farm location.
Yeah.
Okay, thank you very much. And